Welcome everyone to ICS 295 on causal reasoning. Today we have a student presentation, Andrew, who will talk about causal discovery. And other than that, if there are questions, let me know before we start. Andrew, you can start sharing your screen. Just to really let you know that homework 3 is now posted, right, Bobak? Yes.
Yes, it's posted.
Okay. And as I said in the email, I would like you to, participation is mandatory for these student presentations. I forgot to mention it earlier. And there might be questions associated with those presentations. So you should stay tuned and ask questions as usual. Okay, Andrew, the floor is yours.
So let me ask, is my screen shared correctly? And also I'm going to be using annotations of it. So
I don't hear you very well. I mean, let me, maybe it's my end.
I move closer to my mic.
Okay.
Is this better?
Yeah, now I hear you. No, it wasn't my end.
Can people also see the annotations I'm trying on screen?
Yeah, I see the annotation that you are making. Yes.
Cool. So hi everyone. So I'm going to be talking today about causal structure learning or causal structure discovery, and I want to start off with talking about a little bit of motivation for what causal discovery is. So let's suppose that we have an alien that decides to visit Earth, and the first thing that they see are the sun and a rooster. So this alien is really curious about what the relationship between the two, these two entities are. So what it does is it decides, oh, let's collect some data about them. So maybe this can be something like, does the sun rise before 6 or does it rise after 6? And similarly for the rooster, does it crow after 6 or before 6? And what it wants to find out is what the relationship between the two are. So whether the sun causes the rooster to crow or if it's vice versa. And so the alien comes up with a bunch of different hypotheses about what the relationship could be. So maybe there's a latent variable that affects both the sun and the rooster. Maybe it's just the rooster affecting the sun completely on its own. It doesn't know. So the goal of causal reasoning or causal discovery here is to try to figure out which graph corresponds with the, or should be corresponding with the data. So I'll just move to the slide. So to get a bigger picture of what causal discovery is, we want to suppose that we're only given the data PV, and the question that we want to answer is how much of the underlying causal diagram can you extract? So we have our real world / nature where we can observe certain data points, and that's going to be our T. But then we also know that from this real world, there's some truth that says, hey, this is how things work. And then this is represented by our causal model. So then the goal of causal discovery is how do you get from the data to that causal model? And that's what we're going to be focusing on today. So then just a bit of review. So for causal structure of a set of variables V, this is just going to be a DAG where the nodes are going to be the distinct elements of the variable, or the distinct elements of V, and where edges are going to be functional relationships between the nodes. And and then this is just the same causal model definition that was given in like week 1 or week 2, where you just have a 4-tuple of V, U, F, and PU. And here's just an example of a causal model, or just like the definition of causal model. The main thing that we're going to be focusing on today is how to come up with the graph rather than the functions. Hello?
Professor, we can't hear you.
Can you repeat?
You cannot hear me now? Do you hear me?
It's better now when you speak this way.
Okay, just to ask you in general to speak slow because it's hard. We don't see your face. You're a little bit in the dark, so we only primarily hear you. So just, it's fine. It's just be conscious of not speaking too fast. And if you can make all your face visible by changing the camera.
Let me, give me like 30 seconds to try and fix the lights.
And then also make the camera show your full face. Right now it's, oh, that's better. Good. You can continue.
It's brighter.
Thank you.
Okay. Yeah, so we have our causal model, which represents these four different, which is represented by a four tuple. And here's an example on the right-hand side. So this should be all reviewed from the past weeks. But then the question we want to ask now is, does correlation between two variables, for example, X and Y here, what can we say about the causal structure from the correlation? So if you only know that X and Y are correlated somehow, then it kind of makes sense that we can't really say much about it. So it can be either that X influences Y or Y influences X. There might be a latent variable. There might not be a direct dependence from X to Y, and you might only have the latent variable here. So then the question becomes, how do we learn this causal structure? So today, what I want to be focusing on is a constraint-based structure learning method called PC and IC algorithm, and kind of extending that to work with, or kind of like take into account more expressibility with latent variables later on called IC star. But I'll start with an example to kind of guide everything through. For completeness, I want to mention that there's two other methods, based on what I've read so far, there's two other like classes of methods for learning causal structure, and that's going to be score-based methods and function-based methods. I haven't read too much about them, but it's just, and I'm not going to cover them, but it's just mentioned here for completeness. So then going back with the data that the alien was having before, in our motivating example, one of the very first things that the alien can check is whether the two entities are independent or not. So then let me ask everyone, what's the easiest way for the alien to check whether the two are independent? If anyone can give an answer.
So you would just count up the frequencies in which each of them occur, use that as your probabilities, and see if the total probabilities of their joint occurrence is equal to the probabilities of each one multiplied by each other.
Exactly. So then, did I have it? Yeah, so essentially what we want to be doing is we want to just check by the definition of independence. So we can kind of easily check this right here, saying, okay, there's 4 entries out of 9 where both of these are both of the sun and the rooster equal to 1. There's 1, 2, 3, 4, 5 entries where the sun is equal to 1, and there's 1, 2, 3, 4, 5 entries where the rooster is equal to 1. So through quick math, you can kind of see that they're not equal to one another. So they're not going to be independent of one another. So then about the hypotheses that the alien might have had from before, it means that we can essentially just rule out this hypothesis because we know that they're not independent of one another. But that's kind of all we can say at this point. We can't really do more without having more information from other variables. So then let's go to another kind of more complicated example where you have these variables W, X, Y, and Z. And suppose that this is the true model that is there's certain independencies that we can kind of tell from this graph, right? The first one would, or kind of maybe the easiest one to look at, is the relationship between X and Y. So we know that X and Y are going to be independent of one another if we're given just W, because W is the common cause, right? On the other hand, we can talk about what or how X and Y are not going to be.
Am I the only one where he's breaking up a little bit?
Or I think my computer was lagging a little bit. But let me just kind of like go back 10 seconds and we talk. So we can also figure out that X and Y are not independent on their own. So if we're not given anything, then they're going to be dependent. There's only one other independency in this graph. Can anyone figure it out?
It's that Z is independent of W given X and Y.
I think my computer was slowing down a little bit. I didn't catch what anyone said.
So Z is independent of W given X and Y.
Yeah. Right. Oh, it is. Can people hear me, or is my Zoom frozen?
I can hear you.
Okay, because my Zoom is just kind of looks like it's stalling, but anyway, so and here's a few other ones that you can also figure out. But the key point here is that the data has to have these independencies and dependencies for this for our graph to be a compatible graph for the system. So then I want to move on to talking about a few of the assumptions that we're going to be making as we're learning the structure of a causal diagram. And these two assumptions are called minimality and faithfulness. So for minimality, the idea is that if we have two graphs, G1 and G2, that can both generate the same distributions PV, then, and we know that G1 is going to generate any distribution that G2 generates, then we're going to prefer G2, right? So the intuition here is that we want the most constrained model for our distribution. And maybe pictorially, you can think of it like maybe G1 generates this set of PVs, but then G2 is going to only generate this set of PVs. So then you want the one that's kind of the most simplest model. Okay, so that's what minimality is. For faithfulness, the idea are it's also called stability in some other sources, but the idea is that we want the underlying natural generator to not give any independencies that are not immediately visible from the graphical model. What this essentially means is that if we know that X and Y are independent of one another, then our graph does not actually have an edge from X to Y or vice versa. Okay. So then I want to go through a kind of like more of an example through what we can do or how we can learn a causal diagram. So let's suppose that this is our true model, which encodes all the independencies in PV. And so then if we make no assumptions about the graph or no assumptions about the about the relations between each of the variables W, X, Y, and Z, what we can figure out is, or the only thing we can kind of say is that everything is dependent on one another, right? Basically, we can't, if we don't know anything about the data, then we can't make any assumptions about the variables. So we start off with a complete graph where everything is connected to everything else. And then what we want to ask is, what parts of this graph can we start reconstructing? Okay. Does it make sense so far? Yes.
Did he drop?
We lost him.
Maybe should turn off the video because that might help him a little bit. I know it was helping Professor Dactor when she was in Israel.
So turn off and turn on because his video, but not the screen, you mean? So how can we see his screen without having a video?
No, I'm talking about us. We turn off our videos.
Our video. Okay, I see. This can help. Okay. But let's see that he comes back again. Okay, stop video. What should we do then? Let me stop recording maybe, or not. I will stop recording.
You can pause it. I think there's an option to pause.
Stop recording. I have only stopping. Stopping. I don't have pausing. There's an option. If I can see.
After a while, that the Zoom died. So
Go ahead. You can continue.
Maybe my internet is not that stable, so I will close video so that maybe the bandwidth is better here. Where did I leave off? Did I get to this slide before I cut out?
You were before this, Andrew. You were talking about how we can reconstruct from full interconnectivity.
Yeah. How we can? You started with the full graph, and then you say, let's see how we can reconstruct part of it.
Okay. Yeah. So I guess this is where my Zoom started dying. Let's kind of start from here then. So then, yeah, we have the full graph here and the complete graph here. And what we want to do is we want to try to reconstruct parts of this graph. So then from before, we know that X and Y are going to be independent given W, and W and Z are going to be independent given X and Y. So we can kind of figure out that because X and Y are independent of one another, this edge between X and Y can't exist, because if it did exist, then even if we blocked on W, we would find that X and Y are dependent of one another. And so we're going to get rid of this edge because even if we don't know the directionality of the other edges here, we can get rid of it because we know that it just can't be there to satisfy this independence statement. Similarly, for the second independence statement, we know that W and Z are going to be independent given X and Y. So then we can get rid of this edge between W and Z. And then this comes to our current best guess, or we update our current best guess to be this graph right here. So then the question now, or I guess, yeah, from this graph, we can't take out any more edges because regardless of what combinations of independent statements we try, we'll find that they are dependent on one another. For example, like for this W to Y, we'll find that W and Y are dependent. So we can't remove, we're not going to be able to remove this edge. So then now the next step is going to be reasoning about any of the edge directions. So can we say that X goes to Z or Z goes to X. And so then the key here is that we want to reuse these independent statements and ask about the variables that are not there. So in particular, for this first independent statement, we know that X and Y are going to be independent if we're given W. And most notably, Z is not in this independent statement. So then what this means is that if we look at all of the possibilities of the chain X, C, and Y, and we just list them all out like this, what we're going to find is that we have a causal chain here, and common effect here, all of which cannot be blocked, or all of this where Z cannot be blocked on to separate X and Y. So then all of these are dependent. So they're all just not possible. And then by process of elimination, you can say that the only one left is going to be the collider on Z. So we can change these edges to become colliders. And that's what we do here. So then at this step, can we do anything else? Right. So it turns out that because this second statement here, it has all of these variables, so we can't use any we can't use the same trick with the colliders here. So then this kind of brings us to the notion of an equivalence class, where essentially an equivalence class is the set of all possible graphs that are compatible with the set of constraints that we have from the data. So pictorially, what this means is that, if you just take this graph here and just list out all the different possibilities for all the edges, then it's a set of all possible graphs, basically. At this step, does anyone see any issues with this slide?
Yeah, the second one, W, where W is a collider, shouldn't be allowed because we know that it's X and Y are independent given W. Whereas if it was a collider, they would be dependent. Exactly.
So then the second one is not compatible because of this, because of the statement too. And so the actual equivalence class for this graph is just these three graphs here. By the way, I'll be monitoring chat. So then if you want to say stuff in chat, then feel free, because I'll see it basically. But yeah, so this brings us to the PC/IC algorithm, which is just the algorithm to actually, or one of the first algorithms to just kind of like learn this causal structure. So the assumption that we make in this algorithm is that the true model that we're going to kind of base everything on does not have any latent variables and is also acyclic.
Just a second, Andrew. So is this the algorithm by Verma and Perl? Perl and Verma?
This, I think PC was Peter and
no, this is IC. There is IC and PC, right?
My understanding was that PC and IC were kind of just two different names for the same, because PC I think was Peter and Clark for the authors, and then IC is just inductive
Inductive causation algorithm, I'm just quoting the paper that you refer to, A Theory of Inferred Causation by Perl and Verma. The algorithm that they are presenting is called IC algorithm, inductive causation. So I think this, I don't know what is PC, probably it's the same one, but it's always good to really, when you are presenting, to credit, I mean, the people and some of the history if it's available to you. So I was just curious. Go on.
Okay. I can add in the links later on, or I can add in references later on. Yeah, so for this algorithm, the assumption that we're going to make is that the true model that we're using it doesn't have any latent variables, and it's going to also be acyclic. And so it kind of proceeds in three different steps. Or not counting the very first one, which just initializes this empty graph G. The first step is going to be kind of looking at which edges we can remove or which edges have to be there, right? So then in our example, we started from the complete graph and we started taking out edges. The IC algorithm here, what it does is it starts from the empty graph and then starts adding in edges until we get to the graph where only the edges that we care about are there in G. So each pair, for every single pair A, B, and V, what we're going to do is we're going to try to find some subset of variables that will separate the two. And if we can't find any such subset, then we're just going to add that edge to the graph G. So that's the first step. For the second kind of phase in this algorithm, what we're going to do is we're going to try to see, or we're going to try to leverage the fact that colliders will naturally block. So then for every pair of non-adjacent variables A and B, if they have this common neighbor C, we're going to check, is C in AB's separating set? And if it's not, then we're going to make C a collider of A and B. So this is kind of saying if C doesn't have to be conditioned upon to separate A and B, then we can make that C kind of that natural collider between A and B. For the third step, the first two steps kind of start creating a bit of a graph. In the third step, the idea is that we want to start orienting as many of the undirected edges as we can, such that two conditions hold. The first one is that the orientation doesn't add any colliders that would have been found from step 2, and the orientation doesn't create any directed cycle, so things still stay acyclic. So then I kind of just made a note up here about what the conditions are, but for this third rule, it's a little bit vague about what it actually wants. So then there's actually 4 different rules that are used to talk about orienting edges from the previous slide. So I'm not going to go over the rules right here because I have the next 4 slides to do that. But this is kind of just a summary slide to just have all the rules in one place. I'll kind of like start off with talking about each rule and why each rule is valid, I guess. So for rule 1, if we know that there's this edge from A to B, and we know that A and C are not adjacent to one another, what we can do is we can orient this edge from B to C, essentially. And the reasoning for why is going to be, well, let's try to orient it the opposite way, right? If we orient it the opposite way, then we're going to get this collider on B, and that's not going to be allowed, or we don't want to add new colliders here. Okay. For the second rule, the idea is that if we have this edge A to B here, and we have this chain or ACB, I should draw the arrows, then what we can do is we can orient A going to B like this. And once again, we can look at what happens if we orient the other way. And specifically, there's a cycle here. Does this make sense so far?
Yeah, just one question here though. Since we don't want to create colliders, we do end up creating a collider here with B, right?
Yeah, so the thing is that creating the collider on B in this case doesn't matter because A and C because there's already a dependence from A to C, right? So then because the two are going to be dependent, it doesn't matter if we block here or we don't block here. We'll always have this path to go to as well.
Okay, cool.
So A and C are already dependent. So the fact that there is a collider will not add a dependency. It's already there.
And actually, I have that same statement about rule 4, but I didn't catch it for rule 2 and 3 beforehand. But I'll get to that then. If that, or if the first two rules make sense, then that's good because these two are the simple rules. The third rule is a little bit more complex, but all it says is that if we have A going to, or an A undirected to C and C going to B, and A undirected to D and D going to B, then we want to orient the edge AB so that A points to B. And we also have the condition that C and D can't be adjacent as well. Like before, the way we're going to figure this out is, or the way we reason about this is by looking at the alternatives. So suppose that we orient B going to A like this, right? If we do this and then then we have to decide, okay, what do we put for, let's decide like what do we put for A and C and A and D? If we put A going to C, then this creates a cycle, so that's not allowed. So then we're going to try putting, so that means we have to put C going to A. So then now the next option is you need to decide, do you want to go A to D or D to A? If you go A to D, then this creates a cycle here. But if you go D to A here, then you're making the collider here. So then basically this kind of is the set of all possibilities if you went from B to A, and they're all not possible. Any questions?
I think it's clear.
Okay, so then the fourth rule is that if we have this path or this chain AC, A undirected to C and C going towards D, and we have a directed chain from C to D and D to B, such that B and C, these two are not adjacent, and A and D, they are adjacent. What we want to do is we want to orient this edge A going to B. And the stars just represent wildcards. So it essentially means we don't care if there's an arrow there or not. So then just like before, we kind of reason about this by considering the alternatives. If we had oriented edge A or B going to A, the edge from the undirected edge from A to B, so that it goes this direction here. There's only two different possibilities for the edge AC. Either it goes down or it goes up like this. If it goes down, then we have a cycle. If it goes up, then we have a collider. So then this is actually the slide where I kind of realized, hey, this might create a collider on B, right? You can kind of see that the two edges are pointing towards B. So we might think that it's a problem, but it actually doesn't matter just because A and D are already dependent upon one another. So we're not adding any dependencies by putting this collider here. Okay. Does this make sense so far? Otherwise, I'm going to start talking a little bit about adding latent variables.
Sounds good.
Sounds good. Cool.
Yes.
So now now let's try to add in latent variables. So what happens if we run the IC algorithm on a model that has latent variables? For example, this one where Z goes to X and X and Y, X goes to Y, and X also has a confounding variable between them. So then if we run that same algorithm on these three variables, what we're going to find is that it's essentially just a complete graph, right? Obviously, because of the edge Z to X here and X to Y, we know that this edge and this edge, there's going to be some dependence between X and Z and some dependence between Y and X. But then for X or Z and Y, what we can kind of easily tell from the graph is that it doesn't matter if we block on X or not, there's always going to be a path from Z to Y. So then because the two are you're not going to find independence by looking at the data. We're going to have to add this edge between Z and Y. So then the issue here is that the edges no longer represent direct causation. To deal with this, we're going to introduce this notion of a partial DAG or PDAG, which is this special type of DAG with 4 different types of edges. The 4 different types of edges kind of represent different information about the underlying causal model. The first type is that we have a marked arrow, so an arrow with a star above it. I tried drawing the star as best as I could, but it just kind of always ended up a bit too high up. So be careful if you're reading the text for this. But the marked arrow star basically signifies that there's a direct path from A to B. So, as an example, maybe I should have done this in the graphs here, but because we have a direct path from Z to X, what we can say is that there's a marked path from Z to X like this. For the unmarked arrow A to B, it means that either there's a directed path or some type or some latent variable or both of them. We don't know. So this edge over here from X to Y, it basically means, okay, well, there could be that the true model may have a direct dependence between X and Y, or there might be a latent variable here. For bidirected edge, this just means that you have a latent common cause. And then if you have an undirected edge A to B, it means that, or A undirected to B, like this, it means we basically don't know anything. It can be a latent variable, it can be A to B, it can be B to A. Okay. So then this kind of gives rise to IC star algorithm, which is similar to IC in many ways, but the only real difference is the third step. So all of this is exactly the same as an IC. In the third step, what we're going to do is in the resulting PDAG that we have, we're going to try to add as many arrowheads as we can and mark as many edges as possible. And these are going to be the 2 rules that we're going to use to do so. Similar to before, I'll be going over the rules here, but I want to make a short note on the notation here. So we're kind of overloading the use of the star. So if we have a star above the arrow, that means we have a directed path. But then if we have a star kind of to the side, like at the end of at the end of an edge, then it represents a wildcard. So we don't really care what arrow is there. So for example, A star arrow B can be either the bidirectional from bidirectional between A and B, or if the arrow isn't there, then it's just A going to B. So then for the first rule, the idea is that if we know that there's A star and then some edge to B, and that there's B edge and then star going to C, then we can orient this edge B to C so that it becomes that directed it becomes that directed edge from B to C. So essentially what we're saying is that there can't be any latent variables between B and C in this case. Or yeah, we're eliminating the fact that, or the possibility of latent variables confounding B and C.
Andrew, I have a question. So I didn't get what is the difference between an arrow that starts with a star, and an arrow that ends with a star.
Oh, so if you start with, okay, so if you have star arrow like this, it means that we just don't care on this left-hand side whether there's an arrow or not. If you have a star, or if you have A arrow star B, for example, oh, that kind of went out messy. A arrow star B, what that means is that you can have A arrow B, or you can have A B going to A. So basically, the wild card is saying we don't care what's there. whether there's an arrow there or not.
So,
Sure.
okay, okay. Okay.
Does that make sense? Or I think when I was going through them, the stars kind of also were a little bit confusing, especially with the new definition of the partial diag here, which allows for a lot of more different possibilities, but it took a while looking at the partial diag here to kind of gain an intuition for the difference.
So it makes sense after a while, you say.
Yeah, I think, yeah, I think it just gets a little bit confusing because there's a lot of new different notations and encodings in the DAG, but it's just kind of like staring at it for a long time. That helps. Should I go back to this slide, or is there some other clarification that people would like?
So you move for rule 1, you move from the left-hand side to the right-hand side. The difference is that the star went from the being next to C being on top of the arrow. What is this? So this is more restricted. What is B arrow with a star means what? Can you remind me?
So this part just means that we know that there's some type of edge between B and C, but then over here we don't care if there's an arrow or if it's not arrow.
Yes, and on the right hand side, so what I'm asking is on the right side, B arrow C when the star is in the middle. What can you remind what this is?
So this means that there's a directed edge. So that means that there may be other nodes along the way, but essentially you're going in a directed path all the time.
There is a directed path. Okay, okay.
Yeah.
Okay.
Yeah.
It could be, so you're saying it could be a chain, but as long as the chain is directed in one direction, it's fine.
Exactly. And that's the point of the star here. If we didn't have, or if we didn't have any markings, for example, in this A going to B, then what it means is that it can be either a directed path from A to B, or it can be the latent variable between A and B. Let me kind of go back to the partial diag here. So if you have an unmarked arrow, then that means either directed path or latent variable.
Okay.
Right. But then if you have the marked arrow, we're kind of constraining it to say, hey, there must be a directed path from A to B.
Okay.
So with this slide, essentially what we're saying is that we can constrain this to just become the directed path here. And like before, we can kind of look at what happens if we did the alternative. So for all of these examples, basically we would come up with colliders on B. So that's why it's not possible, and I'm not going to go over all of them, but that's the intuition. For rule 2, the idea is that if we know that A and B are adjacent and there's a directed path somehow from A to B, that's obviously not going, that's obviously not like just like this. What we can say is that this edge A star B must go must be star arrow B. Basically, we're just eliminating, the idea is that we're eliminating this cycle that would appear if we oriented the other way. So that's the idea behind rule 2. In general, for IC star, rule 1 is a much stronger, it constrains the graph a lot more strongly than for rule 2. But then one kind of quick example that I want to go through before I run out of time here is with this kind of like with this example. So suppose we have our true model again at the top and our current best guess at the bottom. We once again start with the complete graph because it's easier to visualize. And we remove all the edges where we know that there's some dependencies. So we have X independent of Y given W, W independent of Z given X and Y, and all three variables, W, X, and Y independent of V given Z. So I've kind of color coded it. I don't know if the color coding goes off well, but this one's this edge, this one's this edge, and then the red ones are just this, and this edge. So we can just remove all of those edges. And this is all done in the first step of the IC algorithm as well. Similarly, we're going to try to find as many colliders as we can. So kind of exact same logics as before. We're going to replace X going to C and Y going to C, or we're going to find X going to C and Y going to C. So then the idea here now is kind of like, we can't really do much more with just the normal IC algorithm. What can we do with IC star? So then I was intending to ask about what the best option was, or which rule we can apply here. But for the sake of time, I'll just kind of say that rule 1 is the one that we want to be using here. And it's because of this path C or XCV, because we know that, or basically we don't know anything about this edge here, but we know that we can find that there's, we can learn that, actually, let me go to the next slide because I've kind of written it out here. That since all of these conditions are true, we can change this V or this Z to go to V with a directed path. And that it turns out that that's the only thing that's kind of the only difference, the only additional thing we can do with the IC star for this particular graph. So then I wanted to talk a little bit about the equivalence class here. So then if this is our current guess of the model, what that means is that this is going, or some of the graphs that could be in the same equivalence class as this is going to be this graph over here, where we've just gotten rid of the directed edge from Z to V, and we said, or let's make this direct causation, or direct causation. By the way, these 4 graphs on the bottom are not PDAGs anymore. These are just the regular true model, or like best guess of the true models that we can get. But this top one is a PDAG. So these arrows actually do mean direct causation. We can orient the edge from the 2 edges at the top, so that go X to W, W to Y. Because this edge is kind of undirected, it means that we know nothing about it. So it can mean that we have both the latent variable here and direct cause between from W to X. And because there's just an edge here, it means that either there's a direct path from X to Z, or there could be a latent variable between X and Z. Right, and I've kind of just summarized the rules really, really shortly here. But does this make sense?
Yeah. Yeah, I think it's maybe there could be questions, but I think that could be a good place to stop.
I only have one more slide.
So you have only one more slide. Okay.
Yeah. One more slide and then summary, and then that's it.
Go ahead.
So if I can get like maybe 2 to 3 minutes of people's time.
Okay.
I'll try to be fast though.
Sure. Okay,
so then in a lot of situations, so we only really care about the relationship between 2 variables, although there might be thousands of variables in some system that we're looking at. So consider the example with the sleep and dementia that was on the previous homework. There's a bunch of variables that the studies kind of reference, but we really only care about the relationship between X and Y. So then the constraint-based approach to determining the relationship between X and Y is going to be first checking if the 2 are going to be independent, and if they are, then you're kind of done. If they're not, then what you need to do is you need to look at the variables in the system that are correlated with the X and Y, and then try to learn enough information about the graph, or enough information about the graph so that you can orient that edge X to Y. or either that or until all your data becomes used. One thing that I'll quickly mention is that you repeat this until you do repeat this step, but then you actually use, or it's better to use a slightly different algorithm called FCI. And the reason why you would use FCI instead of IC star or IC is that this one uses a slightly different encoding called a PAG, but it's a lot more, it's able to express a lot more of the relationships between variables. It's able to be a bit more precise with that. And I'm not going to go over this at all, but it's just a quick mention. So then the summary for this entire presentation is that by using conditional independence constraints, we can extract partial information about underlying graphical structure, but it's not always going to be sufficient to extract the entire full graph of the true model. So then recent research in the area of causal discovery has kind of looked into expressing things as PAGs and kind of the different notions in there, so that we can identify different properties like identifiability. Yeah. And yeah, here's some references at the end, and that's end of the slideshow.
Okay, great. Thank you. Thank you very much. Okay, good. So we will post all of this. I think it's already maybe posted on the class page. Okay, good. So see you next on Wednesday. I will be presenting.